Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on DC3 as we focus on science lessons. I'm your teacher, Javid Wilson. Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on VC3 as we focus on science lessons. I'm your teacher, Javid Wilson.
Channel 114.
Good morning, boys and girls. Do you know what this is? Do you want to avoid getting shocked? Tune in on VC3 as we focus on science lessons. I'm your teacher, Javid Wilson.
Good day, everyone. I am Nicole Paris, your math teacher. I'm inviting you to tune into VC3 Weekly. Let's make maths fun. Remember, math matters.
Good day, students. Welcome back. Today, let us practice a CSEC past paper question on solving simultaneous equations using matrices. So on the board, I have the question for you, which is using the matrix method, solve the simultaneous equations 2x plus 3y equal to 5 minus 5x plus y equal to 30. Previously, when we looked at solving simultaneous equations using matrices, we developed a three-step method. So I'm going to write the 3 steps so we have something to remember what we need to do. Let's first of all take this simultaneous equation and put it in matrices form first. Okay, let's put it in matrices form first. So to put this in matrices form, we said we need to have 3 matrices. The first one will be the matrix with the coefficients, and the coefficients would come from the letters, and we put that in order. So the first matrix would be 2, minus 5, 3, and 1. So that's our first matrix. And then the second matrix would be the matrix with the letters. So the matrix with the letters in order would be X followed by Y. And we're going to write this as a column matrix, so this will be X, Y. Okay? Where it has only 2 rows, 1 column. And then we have our third matrix, which is the number matrix, the answer matrix, which will comprise of 5 and 30. So that is our simultaneous equation written in matrices form. Now let's revise the steps that we need to use for solving the simultaneous equation using matrices. And we said step 1. Okay, so this is the simultaneous equation written in matrices form. And we are going to give each of these matrix a letter label so that it will be easier for us when we're going to use the different matrices. So, the first one, let's give that the letter label A. This one, let's just put capital letter X. And this one, let's put capital letter B. So we have AX equals to B. Usually that's what you see in the textbook. Okay? So this is A, this is X, and this one is B. So let's look at the steps for solving the simultaneous equation using matrices. Step 1, we're going to find that of A, which is quite simple. We need to use the formula for the determinant. So that means the determinant, and the formula will be bracket subtract bracket. Alright, and in this bracket, the first bracket, we're going to put the product of the leading diagonal elements. So this is the leading diagonal. We put the product for the leading diagonal, which will be 2 times 1. And in the second bracket, we're going to put the product for the elements on the non-leading diagonal. So this will be 3 times minus 5. Okay, let's simplify this. 2 times 1 is 2. Minus 3 times minus 5 gives us minus 15. And when we have 2 minus sign coming together, one after the other, then this is actually multiplication, which changes the minus to plus. So this will be 2 plus 15, which gives me 17. So step 1 is to find the determinant of our A matrix, and that's 17. Step 2, I'll put step 2 here. For step 2, we said that we are going to take the adjoint of the matrix A. So step 2, we need to take the adjoint of the matrix A, and we are going to multiply the adjoint of matrix A with B. So this will be multiplied by B. Adjoint of A, we said, is where we take the elements on the leading diagonal and we're going to swap them. So let's just do that. So the elements on the leading diagonal swap. 1 goes up here and 2 comes down here. So we have 1 and 2. And the elements on the non-leading diagonal, we are going to simply change their signs. So this is minus 3 and this is positive 5. Okay, we don't need to write back the multiplication sign, we just need to understand that they are multiplying. So now we're going to use the matrix for B and put that here. Okay, which will be 5 and 13. Okay, so this is setting it up, adjoint of A multiplied by B. And let me insert here, students, do not change the order of how you multiply this one, okay, because it will not be possible. You must put that B matrix furthest from the right, followed by the adjoint of A, which is on the left. Okay, so now we're going to multiply. Remember, we looked at some different ideas for multiplying. I'm going to use the shorter method, which is the blocking out concept, blocking the matrix, the row that I'm not going to use first. So I'm going to block this row because I'm not going to use that row first. Remember, we have to go by row, multiply by column. So we take the row from the first matrix and the column from the second matrix. So let's multiply. 1 multiplied by 5 gives me 5. minus 3 multiplied by 13 gives me minus 39. So I have minus 39 plus 5. That is going to give me minus 33. No? Minus 33? Okay. So you are on target. It's minus 34. Good? Alright, so we are finished now with this row because we do not have any more columns to multiply with this row. So we move to now our second row. And let's block the first row. Okay? Again, if you cannot do this in your head, you can put it into your calculator, it wouldn't be a problem. So we're going to multiply 5 by 5, which gives me 25. If you want, you can put 25 out in your working column. And then we have 2 by 13, which gives me 26. So I have 25 plus 26, which gives me 51. Good. So when we use the second row, multiplied by our column, we got 51. So that is the product of the adjoint of A and B. Now step 3. Step 3, and remember our main objective for solving this simultaneous equation using matrices is to get the value for x and the value for y so that it balances out what is on the left side of the equations and with what is on the right side of the equation. Alright? So for step 3, to get the values for x and y, we are going to now take step 2 and divide by step 1. Quite straightforward. So step 3 is taking step 2 and divide by step 1, which is our determinant of A. Okay? And this is going to give us the values for x and y. Alright, let's just work it out to see what we get. So this is saying we're going to take minus 34, 51, which is the product for the adjoint of A and B. And we're going to divide that by our determinant, which is 17. Okay? And remember we said here, each of the components in the matrix is going to be divided by the determinant. So 34 will be divided by 17, and 51 will also be divided by 17. So this is equal to now minus 34 divided by 17 gives us minus 2, if my memory serves me well, and 51 divided by 17 will give us simply 3. Okay? And it goes without saying that minus 2 will be for x, therefore, so we conclude therefore, x is equal to minus 2 and y is equal to 3. Alright, if you want to confirm whether or not your solution is correct, you can go and take minus 2 for x and put it there, and if you take 3 for y and put it here, then you're supposed to simplify to give you 5 to the end. And 2 times minus 2 will give us minus 4. You want us to try and work it out. So it becomes 2 brackets minus 2 plus 3 bracket 3, and that we are saying is supposed to be equal to 5. Let's just check to see if we get the same answer on the right. So minus 2 times 2 will give me minus 4, plus 3 times 3, which is 9, equal to 5. Minus 4 plus 5 will equal to, minus 4 plus 9, will equal to 5. So we have confirmed that our answer is correct for the first equation. You can do the same thing for the second equation. So we have minus 5 bracket minus 2 plus bracket 3, which equals to 13. You can punch this like that in your calculator. Forget about the right side, punch the left hand side in the calculator. But let's try. Minus 5 times minus 2 gives us positive 10, because minus and the minus multiply gives positive. 10 plus 3 equals 13. So we have confirmed for both equations that x is minus 2, when x is minus 2 and y is equal to 3, both equations are true. Our balance is up. Alright?
Good day, everybody. I am your language teacher, Miss McGuire. Tune into VC3 every week where you can get live learning sessions. See you there.
Students, welcome back again. Now we are going to look at one of the more difficult parts of matrices topic, which is to solve transformation questions using matrices. So on the board I have the heading, first of all, the identity matrix and solving transformational questions using matrices. And to do this, we're going to first of all explore or develop an understanding of the identity matrix. And then we will look at how to reason types of transformations. And then we're going to combine the use of the identity matrix to solve different types of transformations. Okay? Now the identity matrix is the matrix that has 1 for the leading diagonal elements in a 2x2 matrix, or maybe in a 3x3 matrix. Okay? So first of all, if we have a square matrix, we must have a square matrix. Okay? So we're talking about a square matrix where we have the same number of rows and the same number of columns. But for our level now, we are going to look at the 2x2 matrix. So we have a 2x2 matrix. And we are saying that the identity matrix, a 2x2 identity matrix, is where we have 1 for the elements on the leading diagonal. And if we put it like that, this is what we say is the leading diagonal. And we have 1 there, and we have 1 here. On the non-leading diagonal, we have 0 and 0. Okay? So this is our identity matrix. And what this identity matrix does is that if we use it to multiply another matrix, any other matrix, once both of them are compatible and they can be multiplied, what other matrix you use to multiply, you're going to get it back. So, and since we are going to be looking at transformation, it gives us a bit of, it's best we probably look at having a 2 by 1. Let's have a 2 by 1 matrix to multiply here, because and I use 2 by 1 because usually points are given as 2 by 1 matrix. So let's assume that we have this point. Usually we say the point. Let's say this is the point. Let's say we have a point A, and let's say A is 2, 3. So this is our point A, 2, 3. Now if we put 2, 3 in the matrix form and multiply with the identity, 2, 3. Okay, let's go through the process so that we can get confirmation on what is going to happen. And again, when we are multiplying, we take the row from the first matrix and we take the column from the second matrix. So this is the row that we're going to use first. Let's block. Let's see what happens. And when I multiply, we'll identify some key concepts for us, okay? So we're going to block this second row because we're not using that, and we're going to multiply with that column. Notice here, class, that this is our first row. So whatever I use this row with, whatever I multiply this row by, the answer will go back as first, as the first element in the answer matrix. Okay, and more than likely, because we are multiplying here, a 2 by 2 multiplied by 2 by 1. So given these two are the same, we are going to end up with a 2 by 1 matrix. So we are going to end up with a 2 by 1 matrix where we have 2 rows and 1 column. So back to the concept. This is our first row, and whatever we use with our first row multiplied by this column, we're going to get it back in the first row position. Alright, so let's just see what we get. And this is important again. Now, because 1 is actually the multiplication identity, right? Anything multiplied by 1 will give you that value. So 1 multiplies by 2. Carefully, 1 is going to multiply by this 2 here. So we're going to get back 2, but 0 multiplied by 3 is not going to give us any value because 0 multiplied by any number will give me back 0. So really and truly, I can focus on the fact that this one is only going to affect the first number in this column here. So 1 times 2 will give me back 2, 0 plus 0 times 3 give me back 0. So I end up with 2 as my first value in the result. Now let's use the second column. Okay? For the second column, here we have 0 multiplied by 2. This one will multiply by the second value in the column, that matrix that we multiply. So 1 by 3 will give me back 3. So here we have gotten back the same, point that we multiply the identity matrix 2, right? Now, let us see what happens if we make some small changes to this identity matrix. So we have just looked at what happens if we take the identity matrix to multiply a point. We're going to get back the same point. Alright? Now, let us explore a bit of transformation and see there are 3 types of transformations that we're going to look at this morning. Alright? So for transformation, there are 3 types we're going to look at. The first one is a reflection. So let's look at a reflection. Okay, and there are 4 types of reflections that we're going to look at. The first type of reflection is where we're going to look at a reflection in the line, the mirror line. Let's say y equals to 0. Let's look at the mirror line y equal to 0. Or you can write this as a reflection in the x-axis. Okay? So the line y equal to 0 will also give us a reflection in the x-axis. Good? And we're going to look at a reflection in the mirror line where x is equal to 0, or this will give us a reflection in the y-axis. And then we're going to look at a reflection through the line y equals to x, which is a diagonal slanted line that splits. And if you look at the graph paper I have here, where you have y equal to x will be the line that matches with the same x value and the same y value. So you have 1, 1, 2, 2, 3, 3, 4, 4, and so on. We'll look at the construction of that later. And we're also going to have a reflection in the line y equal to minus x. Okay, so that is our reflection. Let's see if we can come up with an understanding of what happens when we are reflecting through the line y equal to 0 or the x-axis. And in our previous demonstration, we looked at this point A, which is 2, 3. So let us simply plot 2, 3 on this graph, and we are going to then reflect 2, 3 through the line y equal to 0 or the x-axis. So 2, 3, let's plot the point 2, 3. And this is our y-axis, this is our x-axis. Let's put some numbers on these so we get an easier way of counting. So from the origin we move 1, 2, 3, 4. 4 positive on the x, going right, negative on the x, going left. So from the center, move, we get -1, -2, -3, -4. Alright? And we go up on the y, let's go 1, 2, 3, 4, and 5. This will be our y-axis. And if we're coming down, negative, -1, -2, -3, -4, -5. Alright, so let us now plot this point A, which is 2, 3. So A, which is 2, 3, will be 2 positive, 3 up, positive. So 2 positive right, 3 up, positive. So 1, 2, 1, 2, 3. So this is now our point A. Alright, so now we are going to reflect this point A through the x-axis. And when we are reflecting through the x-axis, we are simply going to see how much movement we need to make from where the point is to meet that particular axis that we have to reflect it in. Right? And we always have to move in using the vertical lines and the horizontal lines that we have already in the graph, right? For moving towards the x-axis, that is. So from A, we're going to move to the x-axis, and this is our x-axis, so we come straight down, 1, 2, 3 places down. And likewise, we will move 3 places past that x-axis to get the reflection, because it's a reflection we're doing. So from here, we have to count 3 now. 1, 2, 3. So this is now going to give me the image of A, and I will put A with the dash at the top. Now if you compare this point A with its image, when we reflect when we reflect A through the x-axis, we got, so we took A, this is A, reflected through the x-axis, we're going to get A prime to be at, let's see what's the coordinates for A prime. So this would be from the center, 1, 2 places right, 1, 2, 3 places down. So we got A image to be 2 minus 3. Okay? And if you notice what is happening here, the only number that changes its sign is the number for the y coordinate. Right? The number for the y coordinate, it changes its sign. And no matter what point you get, if you were to reflect that point, we can generalize. If you reflect that point through the x-axis, then you're always going to get the y coordinate changing its sign. Now, let's see how we're going to use matrices now to show that change which happens to the y coordinate. Remember, we want to come up with a matrix that when we multiply the point A with that particular matrix, then the y value is going to change its sign. And the identity matrix is what we use to come up with these transformation matrices. Alright? So, let's just put back what we have here. 1, 0, 0, 1. Multiplied by 2 and 3. And go back to the theoretical part of what we really want. This is our identity. We need to make changes to the identity so that we are going to end up with 2 minus 3 as our result. Okay? This is very interesting. Now, remember when we started looking at the identity matrix and what happens when it multiplies? We said that this first row will give us back the first row value over here. We don't want any changes to happen with the first row value that we get in our answer. We don't want any changes with this. What we want to be changed is the second. So naturally you will just think, well, to get this to become a minus 3, well, we can just simply put a minus there because we cannot get a minus 0. And this second row is what is going to give us the second row value in our answer. So we simply put a minus there. And you can figure this out. So you don't have to memorize all of the matrices that are for transformation. You can work them out, understand them. And if you were to, if you multiply this, you're going to get back whatever is here. So if you block, look, 0 times 2 will give me 0. Minus 1 times 3 gives me minus 3. So this is the matrix that will now represent generally a reflection in the x-axis. Okay, so we can put this here so that we can memorize it. Just to make a better understanding. But that is the matrix that gives us a reflection in the x-axis. And if you come back to our point here, A, if we were to now reflect A in the y-axis, the y-axis is here. So this is my mirror line. Okay? So to reflect A in the y-axis, we now come to the mirror line and pass it the same amount of movement. So from here we go 1, 2. 1, 2. Which gives us now the image here. Let's put double prime for that image. Okay? And if you look at the coordinates for A double prime, when we reflect it in the y-axis, so reflecting it in the y-axis, A double prime will now be, take the coordinates, minus 2, positive 3. Okay? So that is minus 2, positive 3. which means, let's go back to our identity, because we are using our identity and manipulate it. After you manipulate it, it's not going to be your identity anymore, okay? But we're making it into, we're going to now manipulate it to get a matrix that gives us the particular transformation results that we're looking at in the question. So if I have 2, 3, but when I reflect it in the y-axis, it becomes minus 2, 3, okay? Minus 2, 3. Look at it carefully. It is now the first row element you want the sign to change. The value remains the same, but you want the row element sign, the first row element sign to change. This change from positive 2 to negative 2. So naturally you would want to put the minus in the first row for the identity matrix that we're going to manipulate. So you put minus there. So when you multiply, minus 1 times 2 gives us minus 2. We don't need to worry about the 0 anymore because we know 0 times anything gives back 0. Okay? So this is the reflection in the y-axis. Generally, the matrix would be, let's just put it on this side, it would be minus 1, 0, 0, 1. We can go further to even analyze what is happening here, class. Because when we did solving simultaneous equation using matrices, usually, and you can look back at our previous videos. If I have a simultaneous equation like this, let's just say this is let's say this is our simultaneous. Look at it. Because this is the usual order that we have. X, Y, X, Y. Okay? When you take out the numbers, usually the numbers are going to look like this. X, Y, X, Y. That's the coefficient matrix that we developed there. Okay? Because remember we would have taken out 2, 1, 3, and 4. So it's X, Y, X, Y. Then we put the letter matrix and let that equal to the answer matrix. But what I want us to see is that when we are reflecting in the x-axis, which coordinate changes its sign? Y coordinate. So if I put this as the identity, look at it. 1, 0, 0, 1. This X, this Y. So if I'm reflecting, let's erase some of this chapter. If I am reflecting in the x-axis, which value changes sign? Y. So look, that changes its sign. If I'm reflecting in the y-axis, which one changes its sign? X. This one changes its sign. Okay?
Hi boys and girls, how are you today? I am Ian Little and I want you to join me on VC3 as I take you to the part of language arts. You will have lots of fun, so don't forget VC3 every week. Join me right here.
The third line we're going to look at for reflection is through the line y equals to x. Let us first come up with the line y equal to x. And this is not going to be difficult, okay? The line y equal to x, usually when you are drawing a line, you only need 2 points, okay? And you can select an x coordinate and put it into the equation, solve the equation for the other value, which is the y, and put both results and make the point. So if I was to substitute here, x equal to 1, because I choose to use x equal to 1, then 1 takes the place for x, which means y is also going to equal to 1. Okay? So this now gives me the point 1 for x, 1 for y. If you want, you can put this in a table form. Y equal to x, usually CSEC give you this. It's the same idea. So you choose your x value, you get your y value as a result. X and y merge together, they give you the point. So I choose x to be 1. If I choose x to be 1, 1 goes there, y equals to 1. That's what I've just done, so y is 1. Choose another letter, another number for x. So if you choose x equals to, let's say 4, 4 can work, or let's say 2. Let's just take 2. Make it easier for yourself. So x equal to 2, which means y is going to equal to 2. When x gets 2, y is also 2. So my 2 points will be 1, 1, and 2, and 2. You can use other points if you want, but it's not going to make a difference. So let us get the line for 1, 1 and 2, 2. Just one plot those 2 points. So 1, 1, that's there. 2, 2, that's there. Let's draw the line for y equal to x. So this is our line y equal to x. Okay. So this is our line y equal to x. Now we want to reflect this point A to the line y equal to x. And with this one, you cannot really solve it simply by just counting like what we would have done with the reflection in the x-axis and the reflection in the y-axis, because now it is. We have to ensure, one of the rules with the counting idea is to ensure when you meet the mirror line, you meet at a 90-degree angle. So it's difficult for you to, just look at it and say that, okay, it's going to meet here at a 90 degrees or there. So we cannot really count. But common sense will tell us that if we look at this square here, okay, and we want to reflect it to this line, reflect it to this line, because this line is supposed to split this square box here in half. When I reflect it, it will just project on the opposite edge of where this point is. So we can, let's just have it as a taken that basically the reflection is going to be here. So this is going to be A to the, we have 1 prime, 2 prime, let's just put 3 prime, okay? So this is A to the 3rd prime, and if you want, you can put 3 up there to say 3rd prime. Usually you don't put 1, 1, 1, you put the 3rd prime. So this is A, the 3rd image that we're going to get for A, alright? And if you look at it, let's compare both points again. When we reflect it, let me complete this one. When we reflect this point to the line y equal to x, then the image is going to be 1, 2, 3, 1, 2. So we get the image to be 3, 2. Good? So the image is now 3, 2. And you start scratching your head because you're wondering, how can I develop a matrix to give me the reflection of A through this line y equal to x, so that if you compare A is 2, 3, now the images become 3, 2. Now let's see what happens. Let's go back to our basic. So we have the identity matrix 1, 0, 0, 1, and we are multiplying that by 2, 3 to get the result of 3 and 2. Okay? And we always go back to this basic step here. What is happening? The first row comes from this identity. Let's see what happens. When we multiply 1, 0, let's drop this one. Okay. When we multiply 1, 0 by 2, 3, we will get back 2 as our first answer. Alright? Because this multiplies by the 2. But if we want to get back 3 rather than the 2, look at what you can do. Let's just make an exchange with this row values. So if we put the 0 there and we put the 1 there, 0 multiplies by 2 gives me 0. 1 multiplied by 3 gives me 3. So I will get back my first value as 3 because I want this 3 now to come into play. Alright? So I put the 0 on, I swap the 0 and the 1. Good? And since we did that for this row up here, we also need to do it for the second row because we want to get now the 2 to come as our second row value in the result. So this now also exchange the 1 and the 0, so you get 0, 1. And I will go further to explain. So we can appreciate 1 times 2 gives you back 2. Remember, this is second row. So this will go back in second place. You might be saying, well, how did I do that? Let us analyze. Look at what is happening here, class. The line that we are using is the line where y is now equal to x. The line is y equal to x. Our identity that we started with was 1, 0, 0, 1. Let's make sure we understand. When previously we said this one will be for the x, good. And this one will be for the y. Good? Now, remember we are working by row, by column, okay? So, what we have done here, for the first row, we have eliminated this value here. Okay? We eliminated this value here. But this value is what is going to multiply by the y in the column. Okay? So if we know we want to get the y value multiplied in the point, right? So what we're doing now, we're going to say, okay, let's move this value. Remember, this is a value, okay? So let's move 0 there and put x here. So we have interchanged y equal to x, okay? Let's see. Let's put y here and 0 there. Now, when I multiply, remember this is going to become my first row answer. So whatever is in this row we'll go back and force to answer. Understand? So even though you might be saying, oh, well, we take the, well, this is supposed to be for y value. No, it is not going to be for y value. Why? Because this is force row multiplied. So force row multiplied will give us back force row value. But what we have done, we have eliminated the x part of it and keep the y part, because the y is really what we want in the solution. Okay, and if this one doesn't make sense to you, then you can make sense of what this part is, because both of them are, they join with each other, but they can be used in different ways. Okay? And I will show you what I want to express here, class. Look. If I have a point P, know your what? 5, 2. So if this is the point P, which is 5, 2, and I say, take this point P, let's use something else. Let's use 4, 2, because I have it on the graph here. So if P is 4, 2, and I need you to give me the reflection of P to the y equal x line. So I want to reflect P through y equal to x line. You don't need to do all the graph there. Use the theory. Because we have just shown what is happening when we reflect. The x value comes down to be the y, and the y value goes up to be the x. So you can just write your answer here. And the reflection will be P prime will be 2, 4. And you can prove it on the diagram. You can prove it on the diagram if you want to make your life easy. Let's see. P is 4, 2. 1, 2, 3, 4. 1, 2. So this is now my point P. Okay? Let's not be distracted. So P is here. Let's show the image of what we have. P prime is 2, 4 when we reflect it to the line y equal x. So 2, 4, 1, 2, 1, 2, 3, 4. So this is now going to give me P prime. And you can appreciate that if you want to look at these 2 points here, when they meet at the mirror, they meet at 90 degrees. So if you draw the line, and this is one of the tools that you can use as well, because CSEC sometimes give you the point and the image, and you need to say whether or not it's a reflection or not. If you join the line from P to P prime, it meets this mirror at 90 degrees. It meets this mirror line at 90 degrees, and as well, both length from P to the mirror and P prime to the mirror, they're supposed to give you the same length. Okay? So, remember, when CSEC asks you a question, they will ask you either to give them the matrix for the particular reflection. You need to memorize it. So this one is for you to be able to remember how to get the matrix to show that transformation. Alright, and let's just finish up with the reflection to the line y equal to minus x. So this one, we said is 0, 1, 1, 0. Okay? So we want the reflection to the line y equal to minus x. And I think you can figure it out quite easily. Okay? So you want to figure it out. If we have the mirror line where y is equal to minus 1, and in interest of time, to get this mirror line, it means that if the y, whenever the y is positive, the x is negative, but both of them are going to be the same number. Okay? So if we come up with the mirror line for that y equal to minus 1, you see there are two axis on the they're leading this, the first one and the third one. No, the second one and the last one. Because if you look at the quadrant, so this is the second and the fourth quadrant. We have negative x, positive y. We have negative y, positive x. So, again, 2 points are the same, except one is positive and one is negative. And we will see it again. Okay, if we draw that line quickly, draw this line quickly. We draw the line quickly. Right. You would have a better graph paper than I do. Okay, so this is the line y equal to minus x. If I give you the point, let's say this is r. Let's say r is 1, 3. Okay, if r is 1, 3, and you're going to reflect that to the line y equal to minus x, you can come up with the values for the reflection. Because previously, when it is y equal to x, we simply said the x and the y values swap. Now, if it's a line y equal to minus x, they are still going to swap. But appreciate, both of them are going to change their signs. Okay? So you swap them and you change both of them signs. Do it in stages first. Do we swap in first? So 3, 1, 3 becomes 3, 1. And then you change the sign for both of them. This is negative, that is negative. And if we show what is happening here on the diagram, which doesn't look so pretty after all the work. So this is 1, 3, 1, 1, 1, 2, 3. So this is now our point for R. Okay? And remember, we are reflecting it through this line. So please try to visualize this line. So we're reflecting R through this line. And the reflection will be minus 3, minus 1. So minus 3 from here, minus 3, minus 1. This is now going to be R prime. Again, you can see both points, when you connect them, you get that perpendicular angle created where it meets with the mirror. Okay? So, when it is the line y equal to minus x, let's finish up. If we reflect to the line y equal to minus x, if we use the point A, then A, let's say this is the fourth image, okay? I didn't show you A here, but let's just work with this because you already understand that. So A4 would be reflect, swap, minus 3, minus 2. Swap and change sign, okay? So first you swap them, change the signs. Okay? So you can write that down to memorize. Reflection in the line y equal to minus x, you swap and change the sign for both elements. Reflection in the line y equal to x, you just swap the coordinates for the x and y coordinates. Right? If it's reflection in the line y equal y-axis, you change the sign for the x. If it's a reflection in the x-axis, change the sign for the y coordinates. Okay, let's finish this up to come up with the matrix. Okay, so if we have the matrix, the identity matrix 1, 0, 0, 1 to multiply by 2, 3, we want to get minus 3, minus 2 as our answer. Because we swap the elements, and this thing works nicely because whatever you do with the points, the same thing you do in the identity. So here you swap 2, 3 to become 3, 2. Do the same thing with the identity matrix. So these elements are going to swap. So this becomes 1, 0, 1, and this becomes 0, 1, 1, 0. Right? And then it say both members change their sign. So if both members change the sign, it becomes minus and minus. Okay, so this is now our reflection through the mirror line. Y equals to minus x. Good? And we will continue with the rotation.
My name is Raquel Nanton. Please tune in to VC3 as we make science fun, meaningful, and interactive.
Let us continue to solve rotation questions using matrices. Okay, and we're going to look at 4 types of rotation. The rotation first from the 90 degree rotation. We have a 180 degrees rotation, and we have a 270 degrees rotation, and then a 360 degrees rotation. Now we have to first of all understand the facts, things that we need to work with before we can use matrices to solve these rotation angles. The first one is that because the rotation uses 3 things. It uses direction, it uses a center, and it also uses an angle. Okay, all 3 combined will give you 1 rotation. When we are using matrices, the center must be taken from 0, 0. Which is the origin. So we cannot, well, I don't think it has been, a method has been created to solve transformation, rotation questions that are not from the center 0, 0. So it must be from the center 0, 0. The other thing is that the rotation, naturally, we're going to use the anti-clockwise direction. Okay? So these matrices that we're going to look at would be matrix that represents an anti-clockwise rotation. But nonetheless, if we know the amount anti-clockwise, we can do it. Well, we can say that it represents also a clockwise rotation in the reverse of that anti-clockwise rotation. Alright? So we're going to look at these 4 basic rotation values. Okay, now let us use our graph again. So we have the center 0, 0. Let's put some numbers on this. So we have 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4. 1, 2, 3, 4, 5, and 6. Minus 1, minus 2. Minus 4, minus 5. Okay, let's just come up with a point on the graph. Let's say this is the point 2. I like 2, 3. I don't know about you, but I like 2, 3. Let's just come up with the point 2, 3. Okay, this mark is not writing properly. So let's say this is my point K. Okay? Let's just say that is the point K. And K has coordinates 2, 3. So K has coordinates 2 and 3. So we want to come up with a rotation of K 90 degrees anti-clockwise. So our direction will be anti-clockwise. Okay? And we're taking an angle of 90 degrees and our center is 0, 0. Now, when you would have done vectors, so let's create a little link here. When we would have done vectors, if we want to draw the vector for a point, a position vector, more accurately, then let's just use that as our starting point, which is the origin. And let's just put the line segment, which goes like that. Okay? So, we can put an arrow on it to say that's a vector. Alright, but I'm not going to put an arrow because we're not doing vectors, but let's connect some of the understanding. Now we need to make a rotation of 90 degrees in an anti-clockwise direction. So wherever you choose to move K, you have to make sure, first of all, that the length of K, it's not going to change. Okay? We are going to take K and just spin it somewhere in an anti-clockwise direction, but it will fall at a specific position. Okay? So the idea with vector I want to bring here is that you can see that if you take this line and you shift where this point is, the length of the line is not going to change. We're simply going to spin it, rotate it. Alright? That's the first thing. Now when we spin it, remember we want to make 90 degrees and we're in anti-clockwise. So if you use your protractor and you set the center of your protractor here, because we're not doing that for this lesson, but I will still go through it briefly. Set the center of your protractor here and make sure it runs along the line here with the baseline that you have in your protractor. Then you're going to put a mark for 90 degrees on the out surface of the protractor. So you put a mark, let's say the mark is somewhere there, right? Oh, well, that looks off. Let's put it somewhere there. Right? Then you get your ruler going this way, and you measure to get this line, the length of this line, also going this way, and that is going to give you your rotation for 90 degrees. But since we are not going to use that protractor, we simply want to use matrices. And what we see happening here is this class. Look, at this part of the graph, and this is how I understand this best. At this section of the graph, my x value and my y value are positive values. Okay? When you come over on this side, the x value is negative and the y value is positive. So if we have to keep this length, there's only so much ways that we can keep that length. It's either we repeat the same movements, 2 across, 3 up, so we put that on the left side, 2 this way, 3 up. And I'm just going to show you that so you see the visual having an impact. If you go 2 across, 3 up, 1, 2 across, 1, 2, 3 up. If you do that, and you put the mark there, I bet you, when you measure the angle in between there, you're not going to get 90 degrees. Okay? The only other way now is if we were to take the coordinates, and let's just change the order. So we're going to use the x for the y and the y for the x. The y coordinate becomes the x coordinate and the x coordinate becomes the y coordinates. Let's see what happens. So we go from here. Remember we move 3 up y. Let's move 3 to this way. 1, 2, 3. 2 up, 1, 2. And if you draw this now, you're going to appreciate at this point you're going to get the same length for both lines, and you're going to get that 90-degree angle that you really wanted to create in between there. Now, it may be for someone who's a new learner, it may be difficult for you to just grasp that. But that is really what happens, okay? Where the x value and the y value swap with each other. So if we come up with the general rule for this rotation, we see K prime. So when we rotate 90 degrees, K prime is now going to be the coordinate minus 3, positive 2. Okay, minus 3, positive 2. Look at what happens with the original coordinates. You can coin what happens in this and make the same changes with the identity. So if you multiply that adjusted identity matrix with this, you will get back that. Let's coin what happens. What happens here? This is something you can do for the previous classes. 2, 3, what happens with the points here? They what? Swap with each other. So the x and y swap. That's the first thing. So 2, 3 becomes 3, 2. After you swap them, what's the next thing that happened? Which of the coordinate changes its sign? X change sign. So I'm going through this first before we go to the matrix for the rotation of 90. Look, when I have a point, the point is always x followed by y. So whatever the first coordinate is, that's your x coordinate. Okay? Never mind, we would have swapped them. When you swap them, the new point is now 3, 2. 3 is x, 2 is y. And if we change the sign for the x, then 3 will change its sign. Okay? If you go to the identity matrix now, this is your identity. Again, 1, 0, 0, 1. We want to multiply that by 2, 3 to get back minus 3 and 2. So we want to get back minus 3 and 2. We already did this one previously when we looked at the reflection y equal to x. Here, we want these two values to swap in the result. So, naturally, these are going to swap as well. Okay? So, this changes to 0, 1, and this changes to 1, 0. When we multiply that, we are going to get the values to change, to swap with each other. Maybe I should show you the construction of it, but later on you can try it for yourself. And remember, this is your first row, second row. So whatever you use this row to multiply, it will give you the first value in the answer. So if you want to change the first value result in the answer, then we will change this to minus. Okay? So if you want to multiply what we have here now, we multiply this, look, if you block that, 0 times 2 is 0. Minus 1 times 3 gives me minus 3. And 1 by 2 is 2. 0 by 3 is 0. So we end up with the desired result. Okay? So in general, a rotation of 90 degrees anti-clockwise would be using this matrix 0, minus 1, 1, 0. Right, in summary, what happens? When you rotate it, we said that when you rotated 90, we are saying x and y swap. Then x change sign. Write and memorize this. So when you get the question for CXC, if they give you a point and they ask you to tell them what is the image after a rotation 90 degrees anti-clockwise, you can give them the image result from using this small summary. The x and the y values swap. X value changes its sign. And if you were to look at 270 degrees before we go to 180, 270 degrees, it will be now coming this way. And you can appreciate that if it comes this way Down here, you have positive x, negative y. So you are going to get the y value to become negative. X value stay positive. But again, class, they are going to swap. The x and the y values are first going to swap. Alright? You can appreciate it if you were to do it on your graph paper and see what happens. K is 2 across 3 up. If I take 2 across 3 down, when you do that, you are not going to get 270 degrees. But if you do 3 across and 2 down, which is the swapping of the coordinates, 2 across and 3 down. Okay? Here we can appreciate we are going to get flush 90 degrees this way, which is the same as 270 degrees anti-clockwise, which is 90 degrees clockwise. Alright? So you can tell us now what is the matrix for a rotation of 270 degrees. Simply put it, again, you're going to get x and y to swap. So it becomes 0, 1, 1, 0. And now you want the y value to change its sign. Remember the first row gives you back the answer for the x. So if you want the y value to change its sign, it must be changing sign in the second row. So this becomes minus. Alright? You can test it for yourself. I will leave you to test some on your own, see what happens. So K double prime would be 3 minus 2. If you put, you get 2, 3 here. You want to get 3 minus 2 as your answer. Okay? It's just a simple matter of having this row value should be changing sign. This row value will take care of the change in sign because it happens in the second value in your answer. So it must be down here. That one is which takes the minus. So that when you multiply minus 1 by 2, you get minus 2. 0 by 3 is 0. So this gives you back that change in the bottom, in the second part. Okay? And make sure to swap them if you want the coordinate to change. The x and the y to exchange with each other. And now if it's a 180 degrees, if we take K and we rotate it 180 degrees, whether it be anti-clockwise or clockwise, it wouldn't make a difference. And if we rotate this, we're going to have flush a straight line like that. Okay, so we're going to have that straight line like that because it's a complete opposite of whatever it was. Wherever K was, it's now complete opposite of that. So this K, let's say this is the third prime, appreciate it will have the same movements but in the opposite direction. So this is 1, 2, 1, 2, 3, then rotation 180 degrees, 1, 2, negative or left, 1, 2, 3, negative or down. Okay? So the matrix for that would be taking the identity again. Do we see any swapping? Let's try to work it out. So we have 2, 3, now becomes -2 and -3. Is there any swapping? Is there any swapping here? No, there is no swapping of coordinates. The only thing happens is that both coordinate changes their sign. So we have to keep the original identity because there is no swapping. Only when we want swap, we make adjustment to the 0 and the 1 and the 0 in the symbol. Alright? So if we want them to change their sign, both of them changes their sign. So here we get the minus there and we get the minus here. Okay? So this will give us the same x value comes back in x position. Alright, so this becomes -2. And if we multiply 0, 2 is 0, -1 by 3 gives us -3. So we get both of them to change their sign. And write it down. I always suggest and I advise you to write down sharp ways of remembering. So this would be -1, 0, 0, -1. Write down what happens. We already started with this for the 90. You do the same for 270 except for the slight difference. And remember it. So x and y swap. Then what happens? Y changes sign. For 180, what happens? What happens? X and Y change sign. Remember them. Class, remember them. Remember them. So if you're given the question, you can easily write the answer. When you have a point, and they say, oh, take this point and rotate it 180 degrees. In your mind, you already know what is going to be the result. X and Y changes the sign. So you just change the sign for the X and the Y coordinate. And it's that quick. You can, I promise you, if you learn these, you can solve that transformation question using matrices very easily, and you're going to get good marks for it. Okay? Now the last one is where it is 360 degrees. And if we rotate 360 degrees, we are going to end back at the same point we started. So there is not going to be any changes in the point. So we're going to just use the identity in this one. It might seem simple, but I have seen CXC ask you a question. Ask you a question to tell them a matrix that will give you a 360 degrees rotation. And students skip that question. Okay? I trust that you will have done thorough work with this transformation. Solving transformation using matrices, transformation question, and we look forward to your comments.
My name is Raquel Nanton. Please tune in to VC3 as we make science fun, meaningful, and interactive.
Channel 114. Channel 114. This is you.
Good morning, boys and girls. Do you know what this is? Do you want to avoid getting sharp? Tune in on VC3 as we focus on science lessons. I'm your teacher, Javid Wilson.
Welcome to the SVG Virtual Science Classroom. Today, we'll be doing chemistry. My name is Juanita King, and I will be your teacher for today. We will be looking at how to write chemical formulae. I will be sharing with you 6 tips that will help you to write chemical formulae. We will be writing chemical formulae for ionic compounds. Ionic compounds are composed of cations and anions. Cations are positively charged ions, and anions are negatively charged ions. When writing chemical formulae, here is tip number 1. Always write the cations first. Let's take a look at some cations. You have the sodium ion. Notice it has a positive charge. The calcium ion also has a positive charge. The ammonium ion also has a positive charge. So, when you are writing chemical formulae, always place the cation portion first. There is one exception to this rule, and that is when you are writing the chemical formulae for compounds which are derived from organic substances. The second tip is 1 is understood. There is no need to write the number 1. 1 is understood. So for example, remember, we don't write 1. Take a look at this ion. It's the sodium ion. This means that sodium has a single positive charge, but there's no need to write the number 1. We understand that there's a 1 in this ion. So when we write the chemical formula using sodium ion, there is no need to write number 1. Here's an example of what I mean. Right in your kitchen, you will find some salt. Salt is also known as sodium chloride. What is the chemical formula of sodium chloride? Remember tip number 1, write the cation first. So, sodium chloride is made up of the sodium cation, and we write that first, and the chloride ion, Cl-. Always place the positively charged ion first. Now take a look. Let's apply tip number 2. Tip number 2 says we don't write 1. So if we are writing the formula for sodium chloride, the formula would be NaCl. There is no need to write the number 1. Here is another example where there's no need to write the number 1. Let's write the chemical formula for potassium fluoride. Potassium its ion is K plus. The fluoride ion is F minus. Both of these charges would have a number 1, but there's no need to write the number 1. So the formula for potassium fluoride is KF. Here is tip number 3. When the charges carry the same number, the numbers can cancel each other out and become like 1. Here's an example. Let's write the formula for calcium oxide. Calcium, its ion is Ca2 plus. The oxide ion is O2 minus. That's a capital O. So what is the formula of calcium oxide? Based on our tip, remember, both of these charges have the same number. Both of them have the number 2. So we can simplify the formula. So instead of writing Ca2O2, we can simplify that formula to Ca1O1, but we do not write the number 1. So the formula is CaO. Let's take another example. Aluminum nitride. The aluminium ion is Al3 plus. The nitride ion is N3 minus. Both of these ions have the same number on their charges, the number 3. These trees can be divided by 3 to simplify. So they become 1s. So the formula for aluminum nitride is Aln. Here now is tip number 4. I call it the swap and drop method, where you swap the numbers on the charges and drop them into place. Swap and drop. Here's an example. Let's write the formula of aluminum oxide. Do you remember what the aluminum ion is? It is Al3 plus. And the oxide ion is O2 minus. Now take a look. They both have different numbers on their charges. This one has a 3 and this one has a 2. Here's what we're going to do to write the formula. We are going to swap the numbers and drop them into place. So we're going to swap the 3 and the 2 and then drop them into place. So the formula of aluminum oxide is Al swap the number, so we get 2 over here, O, and swap the number 3 and drop it into place. Now what do I mean by drop it into place? Notice that the numbers that are written here are lower This is not correct. Neither is this. So we want you to write those numbers as subscripts. Subscripts, meaning that they are dropped. Here is another example using the swap and drop method. Let's write the formula of potassium oxide. Potassium is K plus, and the oxide ion is O2 minus. Always remember to write a capital O for oxides. Now notice, the potassium has a single charge. The oxide ion has a 2 minus charge. We are going to swap the numbers and then drop them into place. Swap and drop. The only thing we swap is the number. So the 2 goes to the potassium and the 1 goes to the oxide. But we don't write 1 because 1 is understood. So the formula of potassium oxide is K2O. Here now is the next tip. When you are dealing with polyatomic ions or radicals, you place them in brackets if they are receiving a number greater than 1. Place polyatomic ions or radicals into brackets when receiving a number greater than 1. Let's have an example. Let's write the formula of ammonium sulfide. Ammonium sulfide. The ammonium ion is NH4 plus. This is a polyatomic ion because it is made up of many atoms. So polyatomic, many atoms. Let's take a look. In the ammonium ion, we have 1 nitrogen, and bonded to that nitrogen are 4 hydrogens. These are all bonded together, so they exist as one entity with a positive charge. So whenever the nitrogen in ammonia moves, the hydrogens in the ammonia move with it. They come as one package. So we cannot separate them. And whatever happens to the nitrogen must also happen to the 4 hydrogens. The sulfide ion is S2 minus. Let's write the formula for ammonium sulfide. Swap the numbers on the charges and drop them into place. The ammonium ion will be receiving the number 2. 2 is greater than 1. So that means we must place the ammonium ion into brackets and drop the 2 outside of the brackets. The sulfide ion would be receiving the number 1. So we just write S. No need to write 1. 1 is understood. So the formula of ammonium sulfide is, open brackets, NH4, close brackets, 2S. Here's another example of writing formulae involving polyatomic ions. Let's write the formula of calcium sulfate. The calcium ion is Ca2+. The sulfate ion is SO4 2-. That's a capital O. Now take a look at this. Both of these ions have the same number. Which rule applies now? They both have the same number, so we can divide each number by 2 to simplify it. If we divide each number here by 2, then what is the formula of calcium sulfate? CaSO4. Do we need the brackets now? No, because 1 is understood. So we only have one sulfate, so there is no need to write brackets. Let's take another look at writing a chemical formula that has polyatomic ions receiving a number greater than 1. Here's calcium phosphate. Calcium phosphate is found as an anti-caking agent in some powdered substances around your home. Let's write its chemical formula. Calcium again is Ca2+, and the phosphate ion is PO4 3-. Which one of these is the polyatomic ion? The phosphate. It's made up of 1 phosphorus and 4 oxygen atoms, and together they exist together as one entity with a 3- charge. Let's write the formula. We swap the numbers on the charges and drop them into place. So the calcium will be getting the number 3. The phosphate would be receiving the number 2. 2 is greater than 1. So we need to place the ion PO4 in brackets and drop the 2 outside of the brackets. So the formula of calcium phosphate is Ca3 open brackets PO4 close brackets 2. And here is the final tip and the most important one. Learn your ions. As you can see, our whole process of writing chemical formulae involved knowing the ions. If you do not know your ions, you will struggle to write chemical formulae. Please learn your ions. Start by learning at least 3 ions a day. You must learn your ions. So we have just done 6 tips which will help you in writing chemical formulae. Thank you for viewing the SVG Virtual Science Classroom. Bye.
My name is Raquel Nanton. Please tune in to VC3 as we make science fun, meaningful, and interactive.
So we have just done 6 tips which will help you in writing chemical formulae. Now let's practice. Let's look at some substances found around the home and write the chemical formula of compounds in them. Here's a common substance in your home. Inside of it, the active ingredient is sodium fluoride. What is the chemical formula of sodium fluoride? The chemical formula of sodium fluoride, if you got it correct, is NaF. Here is another popular substance found in your home. Inside of it, there is vinegar. Let's write the chemical formula for vinegar. Vinegar is composed of the ethanoate ion and the hydrogen ion. Notice, in this case, I'm writing the hydrogen ion behind the anion because vinegar is an organic acid. So what would be the formula for vinegar? CH3COOH. Incidentally, vinegar is a dilute solution of ethanoic acid, CH3COOH. Here's another common substance found in your home. This has in the chemical sodium phosphate. Let's write the formula. Sodium phosphate. The sodium ion is Na+, and the phosphate ion is PO4 3-. What is the chemical formula of sodium phosphate? If we apply the swap and drop method, then the sodium would get the 3 from the phosphate ion, and the phosphate would get a 1 from the sodium ion. And since we don't write 1, there's no need to bracket the phosphate ion. 1 is understood. So the formula of sodium phosphate is Na3PO4. And here is one more. This common substance found around the home has in baking soda. Baking soda is also known as sodium hydrogen carbonate. Again, the sodium ion is Na+. The hydrogen carbonate ion is HCO3-. What is the formula of sodium hydrogen carbonate, also known as baking soda. You guessed it, NaHCO3. There's no need to write the number 1. There's no need for brackets. Just smash those two ions together. Sodium, hydrogen carbonate, NaHCO3. So that's it. 6 easy tips to help you remember how to write chemical formulae. But the most important one of them all was number 6. Learn your ions. That's the greatest key to success. Thank you for viewing the SVG Virtual Science Classroom. Bye.
Channel 114. Channel 114. Visit you. Channel 114.
Here's your chance to win even more from the National Lotteries Authority when you play for 2 times daily. Choose 4 numbers from 0 to 9 and you can win up to $5,000 with a $1 inline bet.
Make 4 and back it up too. That's right. There'll be lots of cash waiting for you.
Get your tickets Monday to Saturday for the Play 4 midday draw at 1:50 p.m. and the Play 4 night draw 9 p.m. So easy to play.
You'll win even more.
Happy 40th Independence St. Vincent and the Grenadines. Right now, we are standing at the Geese Terminal for the Everything VC Expo 2019. That's being hosted by Invest SVG. Now, it's the second edition of How Much You Know St. Vincent and the Grenadines. And of course, we're going to be looking at many products and services that are found right here, that are created right here in St. Vincent and the Grenadines. And of course, we're going to be asking you guys a ton of the questions just to find out how much you know about St. Vincent and the Grenadines. I'm your host, Crystal Oliver. Let's take a look at the inside. And of course, our first stop is the welcoming table. So on entry, you have the option. Admission is free, yes, but you have the option of making a donation to the World Pediatric Project. Yeah, you know, they do a lot for our children here. Those children who would need surgeries done that they cannot get elsewhere. This is the group that would assist them. So as soon as you're through making your donation to the World Pediatric Project, you can step onto the other side and there is a welcome map. And it has all the booths that are available, numbered from 1 to the very end. Not sure where it ends. It ends at 100. And you can see a list of all the various businesses that can be found on the inside. So yeah, let's make some movement.